Hi, I'm Andy, and welcome to my walkthrough of the 2020 Sands holiday hack. In this video, our main objective is to open the HID lock in the workshop. Both Bushy and Fitzy have some hints that might be useful. Let's go see Bushy first. On our way, we can grab this red light bulb that's laying on the floor. This will come in handy to access the other floors via the elevator later. Bushy is having trouble opening a door of their own. To unlock it, we need to run the door program, but it requires a password to operate. We're also told that there's a couple of other apps for the lights and the vending machine that we can optionally solve too. These two have a config file, but there doesn't seem to be one for the doors app, so that suggests that the password has been hard-coded into the binary. If it's been hard-coded in plain text, then it should be fairly easy to spot. We can extract all the text from a binary using the strings command. This does produce a fair bit of junk, but further down we see the various messages that may be printed to the user, including one which explicitly states the password. We can now run the door app and input this as the password, and we successfully unlock the doors. We'll come back to the lights and vending machine in a moment, but for now, let's grab those few hints from Bushy and step inside. There's a couple more of Santa's elves here, and the room is still quite dark as we've not yet switched on the lights, but we can just make out another item laying on the floor, which turns out to be the missing elevator button. Let's get those lights working. Back in the terminal, the Lights app also asks for a password. The app suggests that this is stored in an encrypted format in the lights.conf config file, and that only selected fields are encrypted. We don't have permissions to edit this file, but a copy is provided in the lab folder to play around with. Let's try changing the password to our own value. And this seems to be accepted. This suggests that the app determines whether a field contains encrypted data or not based on something other than the name of the field. Restoring the lab config file to the original state and reopening again, note that the encrypted password is a string of what looks like hexadecimal digits apart from a prefix of $. Perhaps this is how a field is determined to require decrypting or not. We can test out this theory by swapping the contents of the fields over. The username now contains the password and vice versa. Running the Lights app again shows this theory to be correct, as the area which once displayed the name of the user now contains "computer turn lights on". Presumably this is the decrypted password. As expected, we can enter what was the original username, and it's accepted as the password. With knowledge of the correct password, it's now possible to run the version of the Lights app outside of the lab folder, submit the password, and pick up the achievement for completing this task. Bushy provides a few more hints for the main objective and suggests trying to get the vending machine working too. As with the previous apps, the vending machine app requires a password. Bushy had suggested deleting the config file in the lab version to see what happens, so let's give that a go. The next time we run the app, we're asked to provide our own username and password, which then get written to a newly created config file. The password appears to be encrypted again. Let's poke at that encryption a bit more. Let's delete the config file and try again with both a username and password of AAAA. The output suggests that this is not a simple substitution cipher, as otherwise the encrypted password would have been the same character repeated again and again. So how about AAAA? The encrypted form is almost identical to the all A's, but the last character is different. How about BAAAAAA? Again, this is almost identical to all A's, but the first character is different. This suggests that each character is encrypted in a way which is dependent on its position in the string, but is not dependent on the content of any other characters. This means we can use a process of trial and error to gradually deduce the password. First, Generate new config files with a 1-character password, cycling through all the letters of the alphabet until the encrypted version matches the first character of the target ciphertext. Then, repeat the same process, but for 2-character passwords, where the first character is fixed as the value discovered by the previous step. And continue repeating the process for the whole of the ciphertext. The target ciphertext is 10 characters, and if the plaintext comprises of uppercase, lowercase, and numbers, 62 possible combinations, then a worst-case scenario would deduce the password after just 620 operations. This is still laborious to do manually, so here's a script I wrote that does exactly that. Like the other apps, Vending Machine has a few second delay as it tests the password which has just been set. But fortunately, this pause occurs after the new config file is generated, and we don't actually care for the password being checked or not, so it's possible to fast-track the process by holding down Ctrl-C. This causes the Vending Machine app to terminate as soon as it's created the config file, and the Python code can then check it against the ciphertext straight away. Very quickly, this script deduces the password for the vending machine is CandyCane1. A slightly more graceful solution involves the use of lookup tables, where we calculate the ciphertext for a series of plaintext A's, and a series of B's, and C's, and so on. Then compare each character of the ciphertext with the same position in all of the lookup tables, and find the one that matches. This equates to the plaintext. Repeat the process for each character. But either way, the vending machine can now be activated, and we can head back into the room to see what we can get from the now activated vending machine. It turns out it's out of stock of almost everything apart from some portal candies, which go into our inventory. Before getting stuck into the main challenge, we should stop off in the kitchen and speak with Fitzy for another hint. They're stuck trying to change the colour of the lights on the Christmas tree, which requires connecting to a cloud service via a dial-up modem. We're tasked with completing the dial-up handshake to establish a connection to the phone number provided by Fitzy. Thankfully, I am old enough and was a nerdy enough kid to have the sound of dial-up modems ingrained in my mind, so it only took a little trial and error to recall the correct sequence and timing.
Your lights have been updated.
But even without this knowledge, it's possible to determine the right order by delving into the source code for the app. Within dialup.js, there's a switch statement that acts as a state machine for the puzzle. The correct button press processes the state machine onto the next phase, whereas an incorrect press, or waiting too long to press anything, sends the state machine phase back to 0. After reaching phase 8, a variable called secret is sent along with an AJAX call to verify the answer on the server side. Further up, there's a series of listener functions which get attached to the noise generating buttons. These progress the phase to the next value and add some text to the secret variable. The correct order of button presses follows their appearance in the code, and the inspector tool can be used to confirm which button is which. It's also possible to predict the value of the secret, which will result from successful completion. Once connected, our prediction can be verified by examining the details of that AJAX call. Regardless, Fitzy thanks us and discloses that Santa trusts Shinny up a tree the most. This fact is pretty handy for our main objective, opening the HID-lock in the workshop. En route, we must reconfigure the Santivator to power both the red and the green receptacles to allow access to floor 1.5. Down in the workshop, Minty is working at a sortomatic machine, and to the left is the locked door. Out back in the wrapping room is Noel, and a few objects lying around. A rubber ball, and a Proxmark 3, That was a device mentioned all the way back in the first video, which is able to read, write and simulate ID badges. We can use this to read the ID of someone's badge and replay it to open up a door that they have access to. Based on the information Fitzy gave us after connecting the modem, if Santa trusts Shinny the most, then perhaps that's whose badge might have access to this door. They were out front by the Kringle kiosk. We just need to stand close enough and open up the Proxmark user interface from our badge. Reading a card is a simple command. The key pieces of data are the card number, 6025, and the facility ID, 113. We can now head back into the workshop and use the Proxmark again to simulate an ID card. Here, specifying the facility ID and the card number lifted from Shinny's card. And it works! The door opens and the achievement is registered. There was a talk at this year's KringleCon that goes into more detail on HID hacking. Do check it out if you want to dig deeper into the topic. Past the door is a small dark room, and our movement is somewhat restricted. But we can slowly meander towards the lights at the end, and we emerge from behind the painting in the main entranceway. But our avatar seems to have disappeared. Oh, no wait, any attempt to move around moves Santa instead. Now we finally see what Jack Frost was up to. He was the one who created this appearance-changing painting and sent it to Santa, and he's been using it to take on his appearance in order to disrupt activities at the North Pole. That's all for this video, but leave a comment if you have any questions or if you used a different method for solving any of these puzzles. We'll pick up the story in part 6 and start foiling Jack's evil plan with the help of regular expressions and Splunk. Feel free to take a slight detour on your way and check out some of my other cybersecurity videos, otherwise I'll see you there.